Today we want to start a new topic. We're going to talk about asset values and interest rates. And so anyway, as we start this, let's just talk about interest rates, what those are. I have heard 1 million people, possibly less than 1 million people, I've heard many people talk about interest rates, and here's what they like to say. And you should not write this down because I'm going to tell you something's wrong. Here's what they say. Interest rate, price of money. No. The interest rate is the price of credit. What's the difference? Well, first of all, what do we mean by the price of something? We mean what you have to give up in order to get it, right? And so if we were talking about the price of money is what you have to give up in order to get it. And you can give up your labor services, or you can give up goods and services, products. And so if we talk about the price of money is expressed in terms of the goods and services we give up in order, what we give up in order to get it. That really doesn't sound right. That doesn't sound like the interest rate. Credit is a loan. And so the interest rate, or interest, is what we pay to get a loan. And it could be borrowed money, but you know what? If you borrow something else, some other merchandise, not money, then you still have to pay for the use of that something, and technically that would be interest also. Back in the old days, before there was money, and there was commodity monies and things like this, or just commodities, people would borrow commodities and pay interest for that loan. And nowadays we might use the term rent or something like that. You might go to, well, anyway, don't want to go too far down that path. But people paid for the use of various commodities. So anyway, a loan refers to credit, and the interest rate is the price of credit. And we are eventually, in this unit, going to get around and talk about what determines that price. And guess what? And there'll be a lot of details that go into it, but prices in markets get determined by two things. What are they? Supply and demand. And so we're going to talk about supply and demand for credit, and then that will determine the price of credit, the interest rate. And so anyway, we'll eventually get around to that. There's different ways of thinking about, well, I shouldn't say that. The price of credit's what it is, but it plays various roles in our economy. One is this, it is an incentive to people to postpone spending. Okay. For example, you go to work, you earn $1,000. You got $1,000. What are you going to do with it? Could just go out and spend it. Well, if somebody comes along and says, hey, if you'll loan me that money, I'll give you interest, then what they're really saying about that is, don't spend that money, let me spend it, let me use it, and then I'll pay you back later and you can spend. Right? And so when we get interest, the way we get that interest is we don't spend everything we have, and we postpone our spending until later. And so interest gives us an incentive to do that. And also, let's just say you earn $1,000 and you spend $1,000. And you want to spend more. You want to spend $2,000. You have to go out and borrow. And then you have to pay interest. And so when you go out and pay interest, you're saying, oh man, that hurts. Maybe I ought not to spend. Maybe I ought to wait. And again, we're back to this idea of postponing spending. Okay. And so anyway, this is an important role that is played by interest in our economy. Let's kind of shift gears. We're going to talk about interest a lot in this unit of material, but let's kind of shift gears and start talking about something else that will have interest blended into the discussion. Future value. Okay, and this starts off kind of simple, kind of slow. Suppose that you have P dollars today. I'll put a little dollar sign up there. P, and that could just be any number. It could be $10, $1 million, whatever you want. But let's say you had P dollars today, and then you put that in a bank account, or you invest it in a bond or something like this, and you just let it sit there, and now those dollars sit there, and then you come back 1 year hence, 1 year from today, and you say, hey, how much do I have in that account? Well, F dollars. And by the way, you'll see this all in a few minutes anyway, but I'm using P and F. These are just, symbols like I say X and Y, but I'm using a P because we're talking about the present amount of money, okay, today. And then F, a future amount of money. And so I'm using letters here rather than the number because we're just using generalized notation. Whatever we talk about, if this were $10, the discussion's the same as if it's $1 million. The specific numbers work out differently. So anyway, we're just using these symbols to represent a certain number of dollars in the present, a certain number of dollars in the future. So, how much is this? And the answer is, well, I would get back my P dollars, of course. In the future, I would have the original amount, plus I'd have interest, right? If I put this money in a bank account, and then I go back a year from now, I would get back my P dollars, and I would also get back whatever the interest rate is. I'll use this interest rate percent, and we'll put it in decimals. So like if it's 5%, 0.05. But anyway, so if I go back a year from now, how much would be in my account in the future? My original P dollars plus interest multiplied by that original P dollars. And so if we let that be 5%, and let's say P dollars are $100 today, then I go back at the end of a year, I'd have my original $100 plus 5%, 0.05 times the $100 equals 100 plus 5 equals $105. Everybody with me on that? That's kind of simple, right? And by the way, I could factor a little bit here, and then it would look like this. My F dollars, how much I would have in the future, equals P times 1 plus I. Now, I've taken that dollar sign out of there just because we don't need that forever. Okay? Pretty straightforward, right? Well, what if I go back in 2 years? We've got a simple case there. I went back 1 year from now. What if I go back in 2 years? I put down P dollars today, and then I leave it there, and then I get F dollars, and I wait 2 years. Well then, here's how much is there. It's my original P dollars, and then for the first year, I got interest on that P dollars, and then in the second year, I got interest on that P dollars again. Is that it? Anybody? Can you hear me out there? Perhaps there's a glass wall here. Is that it?
You get interest on interest.
Interest on the interest. So here's what happened. Here's what would happen. I put my money there to work, and it stays there and it works for 1 year. And here's when I would have $105, right? But I don't collect it. I just let it stay there. And so in the second year, I should get interest not only on my original $100, but here's another $5. And so here's the interest on the original $100 for year 2. Here's year 1. But also in year 2, I'll put year 2 here, I get interest on the first year's interest. Right? And this I times P, that was the $5. And so now it's just interest on interest. How much is 5% of $5? Pardon me? 50 cents? 25 cents, right? So that's not a lot, is it? That extra 25 cents. And so what would we have? We would have $100 plus 5% of 100 is $5. 5% of 100 is $5. And 5% of $5 is 25 cents. And so then what would we have? $110.25. Except, we don't have to keep doing it this way. What I could do is do a little bit of factoring, just as I did before. And here's what I get. P times 1 plus, maybe I'll erase a little bit here, plus IP, 2I, okay? And then here's a P and then I squared. Well, that's a nice expression. Now, this is back where you remember in 4th grade and you're saying, why do I have to do that? Learn to factor things? Because this can be simplified to P times, the P isn't being simplified, but this thing right here is 1 plus I to the 2nd power, squared. I don't know if you did that, but that's what I said. 4th grade. Why do I have to be able to factor? I'll never use that again. No, just for the rest of my life. Well, let's go back over here. After 1 year, I haven't put a 1 up there, but that was a 1 up there. P times 1 plus I to the 1st power. After 2 years, P times 1 plus I to the 2nd power. Well, guess what? I can just write a more general formula, and here's what it looks like. F equals P, my original amount of money. F is how much I get back in the future. By the way, I'm going to put a little footnote down, or a subscript down here. I'll say T. T as in some point in the future, some time period. Okay. Equals my original amount of money times 1 plus I, this is the interest rate in decimals, raised to the T power. However many years I have to wait. Now here T is a subscript with the F, and it's just telling us T time, how many years do I have to wait to get my money back. And then this T though, it has a mathematical value. We are raising this 1 plus I to a power. And so if I put that money there and I wait 30 years, then this would be $100 times 1.05, there's my interest. And then if I wait 30 years, 30 is my exponent. Okay, however long you wait, that's how much will be there in that account. I'm not going to do this calculation. I started to do it, but I want to do something else, and I don't want to get sidetracked here. So this is our general formula. The first 2 years, 1 year, 2 years, I kind of expanded that to kind of show you what a person would do. We could have come back here and said, oh, I wait 3 years and then add another IP and then another interest on this interest and then another year's. We could do that. But this is just the general statement right here. So if you invest some money in the present, this is today, how much you invest, 1 is the loneliest number. 1 is just the number 1. The I is the interest rate that we're earning, or the rate of return we're earning in decimals, right? And so then, and T is how long that money is working for us. Okay? And so there's how much would show up in that account later on. Now, we did this, so I want to come back and talk about it just a little bit more. A moment ago, this is 25 cents, you remember? This is interest on interest. What do we call that? Compound interest. Interest on interest is compound interest. What do we call this? Interest on the principal amount. Simple interest. And so here's what we had. We had $10. This is with the 2-year investment. We had $10 in simple interest. And we had 25 cents in compound interest. And you know, you could just, a person could say, gosh, 25 cents, who cares? Almost. Who cares? But here's the deal. Compound interest matters not so much in 2 years and not so much in 3, but over the long term it matters a lot. I just mentioned 30 years. Let's talk about 30 years for just a second. Let's say that we just said, well, compound interest is so small, let's ignore it. And just leave it out of the story. And let's say all we got was simple interest, just interest on our original $100. How much would be there in 30 years? Well, we'd have our original $100, right? And then we'd have $5 in interest a year, simple interest on our principal, our original amount, times 30 years. So that'd be $150. 100 plus 150, 250 bucks. And so if we leave the compound interest off, it makes it a lot simpler, doesn't it, than if we get into all those exponents and things like that. If we leave the compound interest off and just go with the simple interest, we got that number. And you know, if we'd done that here and left the 25 cents off, rather than saying $110.25, we said 110. And you might go, you know, that's close enough for government work. It's not exact, but it's pretty close. So, how close is it if it's a 30-year deal, though? Is it 250? How far off is that 250? And so let me get the old calculator out. And I'll say $100 is my present value of my investment. 5% is the interest rate. I'm going to let it go for 30 years. I'm going to do that again. Couldn't be $14 million, could it? That's not what it showed up. Damn. Okay, I've got a microphone on and I said, damn. Edit that out. $432.19. That's with the compound interest in. Here, with the 2-year deal, it was worth 25 cents, and you could almost ignore it. Wouldn't buy a soda. But the compound interest, what's minus 250? The compound interest in this particular case is what? $182.19? Compound interest is quite a bit then. If I draw you a graph, and I like to draw the graphs, here's what we have. Here's our dollars, and we'll start off with $100. Here's our F. And we'll start off with that amount. And then this is T. And so what we see is this. If we have simple interest, then what happens is every year we get another $5. And if we have compound interest, what happens is it starts going up like that. Okay? And this is simple plus compound interest. This is F plus, what would it be, IT, P. Maybe I should do it in a different order. T, I, P. The number of years multiplied by what? The simple interest. And then this formula is just what I wrote before, equal to F times 1 plus I to the T. And the difference between these two, the vertical distance at any single point in time we want to choose after 1 year, 2 years, 3 years, 5 years, whatever, the difference between those is the compound part. And so, yeah, it's very small, like in 1 year, there's no difference. But After that, what do we have at 2 years? This is 25 cents difference, and yeah, you can't ignore that. But it just gets bigger and bigger. And you know what? The longer it stays, the bigger it gets. And it gets huge over time. And I mean huge. And I will just leave that as an experiment you can perform at home. If you like to expand that, I'll make it go 100 years and see what happens. Oh, I can do that. 100 years. I think it was 150. Yeah. And so then what you would have, well, how much would it be in 100 years if there's only simple interest? It'd be 100 times 5, that's 500 in interest plus your original 100, $600. So this would go to 600. Well, with compound interest, 13,000. So there's $12,500 worth of compound interest. The longer you let that grow, the bigger it gets. Now, so I guess what I'm doing a couple things. One is I'm telling you about this compound interest and sort of showing you how it's growing exponentially. The other thing I'm telling you this is if you hope to live until retirement, you hope to be not poor. And one way of not being poor when you retire is to save money. And the sooner you save, the more that compounding works for you. And if what you do is wait until you're 40, and let's say you want to retire when you're 65, you wait till you're 40, you retire at 65, you save for 20 years, and that compound interest is working for you, yeah. But if you start saving when you're 25 and you retire at 65, then you've got 40 years worth of compounding, and boy, I mean, this thing gets steep. And if you could wait, you know, what was the story about the Europeans that came and bought Manhattan Island from the Indians living there, and they paid like in $12 worth of money, beads. If you took that $12 and invested it for about 600 years, that wouldn't be that long, would it be? How many years would it be? From like 1600 till today. It'd be 400 or 500 years. You invest $12 for 400 or 500 years, and guess what? It runs into billions. And so the longer you put that money away, the more the compounding works for you. And it's not just working for you a little, it's exponential.
But where do you find interest rate at 5%? I mean 5%.
Oh, where do you find interest at 5%? A lot of places. 5% is not an outrageous interest rate.
Like my savings account's like at 0.5 right now.
Your savings account is at 0.5%? Well, that's not where you found it then. Okay, but bonds, corporate bonds, you can buy a mutual fund that's investing. You can buy today, and interest rates change over time, but today the interest rate on 30-year Treasury bonds is how much? 4.2%, 4.25%. So that's not quite, but I mean that is... It's safe, assuming the government doesn't go bankrupt. That is safe, but you could go out to corporations and so forth and buy a corporate bond and get above 5%. And I don't mean to say just any corporation, but you buy ideally a mutual fund that is investing in corporate bonds, and it's investing in corporate bonds from, you know, large companies that have been in business for 100 years or more and are very likely to stay in business, pay their bills, you know, that sell all kinds of products, General Electric and IBM and AT&T and things like that. And so you can get above 5%. Not in your savings account, not in a passbook savings account, probably has no maturity date on it and so forth. Interest rates are low on that right now. But anyway, there's a lot of places to get that. I had bonds issued by banks years ago, and they were paying 12%. And you know, that was pretty good, and there was only one problem, is that bank went out of business. And I got my money back. I didn't really want it back. I wanted it back someday, but I wanted to earn 12% for 30 years. And then they went broke in about 3, so there you go. Anyway, let's go back. I want to use this and talk about something else, a rule of thumb called the Rule of 72. And basically, it's consistent with all this stuff, but it's a rule of thumb. And when we say rule of thumb, we do not mean this is exact out to 6 decimal places and so forth. We're talking about something that is, you know, it's a kind of a rule that you can remember and maybe do some calculations on the back of the envelope sometime when you don't have a calculator with you. And what the rule of 72 is about is this question: how long for my investment to double in value? We've kind of switched gears, a little bit different letters here, but you'll be able to figure this out fine. Annual rate of return, interest if you like, and then T, time for investment to double. Double in value. So, in this particular case, and this is not as exact as what we were doing before, but in this particular case, we're going to let this rate of return, we're going to express that in whole numbers. Okay, if we don't want to do that, we'd have a rule of 0.72. We're not going to do that. Anyway, rule of 72, and so now if we had 5%, we'd just put a 5 up here rather than 0.05. Okay, so anyway, I'm going to take an easier number to work with. Here's what the rule of 72 says. 72 equals, if, let's say we get a 6% rate of return. I put a 6 in my formula, times T, time to double the money. Divide each side of that formula by 6. Cancel, you know about the canceling. And so then that's 12, right? 12 equal T. What's 12 mean? It means this. If you invested some money and it's earning 6% a year, 12 years from now, then you'd have twice as much money. And this is when we don't take anything out, and that's what we were talking about before. We're not taking anything out each year. We're just leaving it there for 12 years, and then there'd be twice as much money. If it were $100, then there'd be $106 after the first year, and the second year there'd be $112.36. There'd be $12 in simple interest after 2 years, and then that 36 cents would be interest on interest. It would be 6% of $6 in the first year, and so forth. And it would grow and it would compound, and then over the years, it would be double. Suppose you get 8%. What's our answer? 72 equals 8 times T. How much is T now? 9 equal T. Now, I express this in terms of an investment. It's not just an investment. Our economy grows, on average, over the long run, the economy, U.S. economy, in real terms, grows about 3% a year. And so if the economy grows 3% a year, and we come back, 72 equals 3 times T, then what we would find out is that in about 24 years, the size of the economy will double in value. Okay? In recent years, we've had, I don't know, let's say 2% inflation. If prices rise 2% a year, then in 36 years, prices will be twice as high as they are today. The average price, not each price. If we go back over a generation, prices have gone up at about a 3% rate. And so if prices rise at a 3% rate, then every 24 years they would double in value. A house that's $100,000 today would be about $200,000 in 24 years. A car that's $20,000 would be $40,000. Okay? Suppose that you weigh 150 pounds. And suppose your weight goes up 2%. How much is that? That's 3 pounds a year, right? And so you weigh 150, and then next year you weigh 153, and you say, you know, that's not much. And so now your weight's going up 2% a year. I'm sorry, yeah, 2% a year. In 36 years, okay, maybe you're 20 today, 36 years, you're 56 years old, and you weigh 300 pounds. What does this mean? 92? When you're 92, you weigh 600 pounds. You don't want to gain 2% a year is what I'm saying. Find that optimum and lock it in. Or just don't grow at a compound rate. Just grow by 1 pound a year, or 2 pounds, or 3 pounds, but don't grow at 2%. That's what will get you is the compound weight gain, right? If you're growing at 2% a year, and if you can just get that simple growth, just an extra 3 pounds a year, you move up this curve. I don't know if this is making any sense to you, because it doesn't make any sense. But the numbers are there, and the numbers make sense. Now, where does this rule of 72 come from? Well, some people just worked with the numbers. I have a colleague that wrote a paper about this. Some people worked with the numbers, and they just came up with it. And how accurate is it? How accurate? Let's do something like this. I've got a calculator. I'll do the calculation. Suppose that we started off with $100 today, and we use that formula we had before. The F equals P times 1 plus I to the T. What our rule of 72 is telling us is this. If this is 0.06 and this is 12, right, there's our rule of 72. It says double your money. Let me do that calculation. I'll say we start off with $100, 6% a year, 12 years. Now, what would our formula tell us that we have in that account? $201.22. So, is that pretty close? You know, that's pretty close. It's pretty close for just being able to pull out a piece of paper and just do this in a few seconds and say, I got an answer. It's not exact. I mean, that's not going to get you through an accounting class or a math class, but that's what the rule of 72 is going to tell us. And so, very often, it's kind of a useful thing to have. What this colleague found out when he did the study is sometimes it depends. Sometimes you're a little bit better off with the rule of 71, and sometimes you're a little bit better off with the rule of 73. You know, that when we're working with rules of thumb, it's not always exact. The problem with 71 and 73 and almost any other number is those are difficult numbers to manipulate in your mind. There's a lot of things that go into 72, though. You can put 2 into it, 3, 4, 6, 8, 9, 12. A lot of numbers will divide into 72. And so it's pretty close. You can just kind of use the rule of 72. Here's when it's further off. When the error is bigger is when these two things, the R and the T, when they are further apart. Okay, when they are like, but if they are close, like 8 and 9, you get a pretty good rule of 72. But if they're further apart, let's just say that you're getting 1% a year. So you start off with $100. Okay. Then, oh, no, what I was going to do is differently. Let's say you got 72% a year. There we go. And you start off with $100 and you get 72% a year. At the end of the year, you got $172. Well, rule of 72 would say, yeah, 1 year it doubles. Well, that's pretty far off. Now we're 28 bucks off. So the rule of 72 is not so good when these are far apart. When they're closer together, it's pretty good. So anyway, there's our story on future value, and there's our story on rule of 72. A couple things I would add to it, and one of them is this, that I use the term compound interest, interest on interest. What I've assumed here is that we compound once a year, that you put the $100 in, it stays there for a year, and now it's $105. I was working to 5%. And then you leave it for another year, and you're getting 5% on the previous year. What if you get compounding every day? What if they were paying interest on a daily basis? What if they took that 5% and divide it by 365 and said, you know, I'm going to pay you that much interest a year. So then we would have daily compounding. We could have monthly compounding, quarterly compounding. And so what I'm saying to you is that we started off with this example up here where we just have, well, not that, that's a rule of 72, but that formula, we were just saying express this on an annual basis, and then that was the end of our story. So, and then what we would say is it's annual compounding. If we want to have more frequent compounding, then we would come in and express both of these things on a different basis. And so if we were compounding, let's say daily, and we're talking about 3 years, then we would express our interest rate, annual rate, 5% divided by 365, and that would go in as the interest rate. And then, if it were 3 years, it would be 3 times 365, that many compounding periods, that many, not years, but compounding periods. If we were compounding on a quarterly basis, then what we'd do is we'd say, oh, well, we'd have 5% divided by 4. So there'd be 4 compounding periods a year. And then, if it were 3 years, then there would be what? 4 quarters per year times 3 years, this would be a 12 power. And so anyway, we can make adjustments to this formula. What we are going to do is use annual compounding, but I just want you to know that there is no sort of problem with this. It's just a matter of how you express these time periods and your interest rate. But once you get the time periods and the interest rate correct, then you can just work with sort of any compounding period you want. Okay. Anyway, one final thing. What would the final thing be? When I talk about interest, I've always used like 5%. We also want to be able to work with fractional interest rates. Like if it's 5.25%, then what we would use in our formula is 0.0525, right? So again, we're always going to be using decimals. And in this formula, not in a rule of 72. And the other thing I would mention to you is this, and this is just terminology of people who do business in financial markets. They would say this is 25, this is the fractional part of a percent, 25 basis points. That's the 0.25. Well, really, this is 500 basis points, right? So the 5.25%, another way of expressing that would be 525 basis points. That's the terminology. 100 basis points per 1%. And that is the terminology used in financial markets to describe interest. And I'm saying that now because there are other occasions when this can come up. Questions about this? Okay. Well, here's the good news. The next topic is just exactly the same as this, only the opposite. Is that the good news? And here's what I mean by that. Let me write the same formula down. We've got some future money, and the value of that future investment, or the value of that investment in the future, is what we start off with today, times 1 plus I to the t power. This would be, and just kind of think about this. Suppose you went to the bank and you said, hey, Mr. Banker, or hey, Miss Banker, I want to give you $100 now, and I'll come back in 3 years or 5 years or 8 years, whatever the number is. I'll come back. How much will be in my account then? And that's what this formula would be for. Sometimes we have investments where that's not the question. Sometimes we have investments where this number is locked in, the future amount. For example, suppose you buy a bond. If you buy a bond today, you hand over some money today, the present amount of money, but the amount you get back in the future, that's locked in. A bond's a contract. It's got the specific amounts of money that you get back on specific dates. And in that particular case, when this is locked in, the future amount of money, oh, I'm buying a bond. It matures. It's worth $1,000 30 years from today. When that is locked in, then the question you start asking is, gosh, how much would I be willing to pay right now? How much would I be willing to put down right now to get that $1,000 30 years from today? So sometimes that's the question we ask. So here's what we do. We say, hey, we got a formula. The thing I want to solve for now is how much am I willing to pay to buy that bond or that future promise of money? The future promise of money is locked in. There's a contract. And so here's what we do. We divide both sides by this thing in parentheses. Right? That's mathematically legal to divide both sides of a formula by the same thing. Over here it cancels. And so let me just rewrite this, and I'm going to reverse sides. But anyway, here's what it says. P equals Ft over 1 plus I to the T. I'm going to annotate this so we've got all the details here. Future value of investment. T years hence. T years from now. We've talked about these other things. This is our rate of return in decimals. Here's the years hence. And then what we would say about this is the present value of F dollars to be received T years from today. T years hence. And just because I don't want to wait until the day before the test, yes, there's the answer, yes, you need to know this formula so you can do the present value calculations. You'll be able to use a financial calculator, yeah. But guess what? There are some calculations that are a little bit sophisticated, and your financial calculator is not fixed up to do that. So, I mean, if you know everything about your financial calculator, you could probably get to an answer. But you can't just like push 4 buttons and say, there's my answer. And so, it wouldn't be bad if you knew that formula and did a couple examples. I will bring you some homework to do. And it won't be where you turn it in for credit, but some homework just for practice so that you'll be able to do this. So anyway, I've got an investment. It's going to give me some money in the future. Suppose that somebody said this to you, hey, I'll give you $1,000 5 years from now. $1,000 5 years from now. Would you give $1,000 for that promise? If you had $1,000 today, would you give it to somebody and say, just give me $1,000 back 5 years from now? No. If you've got $1,000, why give it up to get back $1,000 later? You might have some use for that $1,000 in the meantime, and also you could take that $1,000 and earn some interest on it. And so, no, don't give it to somebody and just say, give it back to me later. And so, the rule that we're going by here is a present dollar is more valuable than a future dollar. That's kind of like saying a bird in the hand's worth two in the bush. Well, here's what we do. If somebody promises you future dollars, we decrease their value when we start talking about when we translate what's their value presently. This process right here, you see how we decrease their value. Here's a promise of some future money. The way we decrease that to see its present value is we divide it by something bigger than 1. This process is called discounting. To present value. Discounting what? Discounting future dollars to present value. Okay. Discounting present or future dollars to their present value. Okay. And you can see that it's discount. We've got a future number, and we're converting it to a present number, but we're dividing that future number by 1. If it were only 1, that'd be the end of it, right? If our interest rate were 0, if we just said, you know, I don't want any interest, I couldn't earn any interest, end of story, then this would be 1 plus 0. Hey, that's 1. And so there would be no discounting, really. A future dollar and a present dollar equally valuable. But as long as there is any interest there, then we're going to divide that future dollar by a number bigger than 1. And so then when we convert it over in today's value, it'll be smaller than that future dollar, the future number of dollars. Let's do a calculation. Let's say something like this. F equals, I don't know, $500, let's say. And let's say the interest rate is equal to, we'll use 5% because we've used it before. And then let's say that the T is, I don't know, 3 years, just 3. And we'll put this into our formula. Present value equals $500 divided by 1.05 to the third power. So here we've converted our denominator, and as I said before, we're going to divide that future amount of money by a number bigger than 1. And here it's about 16%, not quite, 16% bigger than 1. So we're kind of discounting those future dollars by about 16%. But anyway, when we do this, let me do the calculation here. So what, 500 divided by 1.157625. $431.92. And what I'm saying is this, these have equal value to you. If you've got the scales there in your head or in your calculator or whatever, in your financial calculator, and you're saying, gosh, what's equal? If somebody promises me $500 3 years from now, how much would you have to put on the scales over here to make me feel equally good today? And the answer is $431.92, and then the scales will be balanced. And you say, gosh, I don't care if I have $500 3 years from now, or $431.92 today. They're all the same. And if they're not, then this interest rate's not 5%. If you are discounting those at 5% a year, then those are of equal value. And you just flip a coin and say, I don't care which one I get. Any questions about this? This thing right here, this 5%, I told you this term is called discounting to present value. This interest rate right here is called the discount rate. And later in the semester, we will talk about the Federal Reserve, and we'll have a different discount rate. You need to be able to figure out what I'm talking about by the context, how it's being used. But the discount rate is the interest rate that we use in these calculations to reduce future dollars to their present value. And that is what we'll pick up with next time, but we will work more with this present value formula. So long. See you next time.